Okay, so this part of the lecture is a little bit more exciting for me personally. It's going to be a bit more practical, especially in terms of the tools I'm going to try to show you. So actually, before I start, I really wanted to say thank you to Amantafa and the summer school organizers. This is the first lectures I've been given for the summer school. And I was a student where you guys were sitting not that many years ago. So this is kind of interesting for me coming here. And I want to say thank you to them and be kind to me is what I say to you guys. So I'm going to try to do my best here as well. So going to the actual topic, similar in terms of concept of how I was talking about the talk this morning in terms of trying to give you as many tools, as it were, so that you could try to analyze the data in the model yourself. And I'm going to carry on with that similar philosophy out into the heliosphere. And in terms of what we were seeing, or what I was trying to explain earlier in the first lecture, was predominantly everything that was seen within the inner circular images. So in there, that's the circle, inner blue circle is the coronagraph. And inside you can see a smaller coronagraph, perhaps just, that's green, and then an SDO image, or it's probably an SDO image, which is the actual solar surface. So very, very small, very close to the sun. But in fact, the space between the sun and the Earth is massive. And that's the challenge for space weather forecasting. A lot of challenges. There are many others, but this is one of them. And this is what was being addressed by the stereo mission. And these are the cameras from the stereo mission. And these are the two really important, what we call heliospheric images, that are looking at very faint light out into the heliosphere. And so what you're really seeing here is, I mean, we've identified here as where Earth is. There's this bubble here, and you've got bleeding through the CCD. And what you can see is CME is coming all the way through. And there were similar processed movies of this that leakers showed earlier. And so we've got these images, and we've got lots of ways of processing it to really maximize our science return. I just put this in here quickly. It's not on your slides, but I had a question about exactly more about the flux cancellation model from earlier. And so if anyone had any questions from the earlier talk, now's a good time, and I'll try to address them. But this is one that we kind of, one that I wanted to highlight. And it was about the flux cancellation model itself, and what they wanted, the questions was about what's exactly happening. And so what the idea with the flux cancellation is, it's a disappearance of magnetic field of opposite polarity to the neutral line. And so that's the kind of, that's what's kind of happening. And you can read through the details later. And the new version of this talk, I'll put it up on the web. And so you'll have that. So like I say, if any of you got any questions that you hadn't asked, we can go address them now from the first lecture or afterwards. Otherwise, I'm just going to crack on. And so in this talk, I've got 5 kind of main themes, or 3 really main themes of trying to get you up to speed with all the different tools we can try analyzing. And then I'm going to try to break it down, try to give you a bigger picture, actually, of how we try to make this relevant for space weather forecasting. And then try to open up for discussion, if we had time, for what we think we can do for the future, and indeed, you guys, what you think you'd like to bring, or what you think we should try attacking. And so the main theme of this is we want to be more practical at this stage, at this particular talk. I'm going to try to talk about it in a practical sense, is we want to find solutions to improve our forecast. And so we want to try to look at all the different types of data sources, and all the different types of ways we can analyze stuff, and trying to think outside the box and try to find solutions. How can we integrate them together? And indeed, the topics that you guys are doing, how can you integrate it with other areas of heliophysics to improve our forecasts? So try to quickly go into the basics of remote sensing, techniques and models. So I wanted to highlight what these big wide cameras, I just want to quickly go over what the stereo mission was doing in case of, you aren't particularly familiar. The stereo mission was launched in 2007, and there are 2 missions, and they both are separating away from Earth at 22 degrees every year. And so they've been going around, and now they're the rear side, and they've come out of conjunction, they're coming back again. If they're both operating or not is, well, we'll go down that another road another time. But the 2 wide cameras that we were showing in my introductory title slide is basically coming from this instrument here, and this is called the Heliophysics imager. It was built at the Rutherford Appleton Lab in the UK, and it's this box here. And what it's doing is it's got these 2 cameras, and it's pointing out into space, and that's what's covering between the sun and the Earth. And it's effectively, if you imagine back in 2010 as an example, you've got one spacecraft here and another spacecraft there, so your A and your B, and they're looking back between the Sun-Earth line using these 2 very large cameras, and you can start doing triangulation techniques, and that's the idea. This is just one example of a movie I created just to highlight the concept of what these cameras are doing, because the title slide was a bit vague. So the 2 wide cameras cover the space between the 2 blue lines here. And so it's covering a really huge elongation width. The inner camera is between the solid line and the dashed line. And that would be equivalent of the solid line here and the dashed line being here. And so this is uniquely different to the coronagraphs because it is further away, and that has unique challenges of being able to, trying to be able to observe very faint light. And in particular, very faint light with a lot of background. The background light, the stray light as it were, on the inner boundary is drastically higher than the background on the outer edge. And that has lots of technological challenges. Okay, so let's go into the elements of some of the techniques that you'll probably see people talking about when they talk about stereo data. And they'll probably, at some point, you'll probably hear people start chatting about J maps. And you'll be going, what on earth is a J? And basically, it's just a height-time map. And that's all you need to think about it. In normal coronagraphic images, when people are looking at estimating the velocity, as an example, for CMEs, you normally have height above the solar surface on the y-axis, and then time, and then you just work out what the velocity is. When you're looking at very large elongation cameras, heliospheric images, height doesn't make sense because it's not a linear thing. What you're observing is not a linear problem. It's an elongation as you rotate and seeing stuff. And so for that reason, you use elongation. And then they start talking about what is a J-mapping technique. But it's ultimately the same thing. It's basically a height-time map, and you try to work out the velocity. And they create these so-called J characteristics. But effectively what's happening is if you take, if they assume this, in this top figure, if you assume the sun is where my green dot is, of the pointer, and everything, all the CMEs and all the solar wind is moving to the left, you'll see solar wind coming out. And what's happening is if you try to track one particular parcel of solar wind, in this case, let's say the red square, it has the equivalent of being at some point on this height time map. And you take these thin strips and you line them along each other for all the different frames. So what you do is if you do that and you track that individual plasma feature, you will see this plasma feature or parts of the CME coming out and making tracks. And it's these tracks is what they're calling is the J tracks because they're not uniquely straight. And so there are lots of techniques of looking at this. And so many of them, there's a few automated algorithms, and most of them are manual. And people start clicking on these tracks to identify how these CMEs or other features move. If you're doing it for a CME, or indeed any kind of plasma packet, you can uniquely get an idea of where it's propagating into the heliosphere and how fast, because of a few assumptions and some basic mathematics. And the reason is because of its trajectory, it might be moving at a constant speed, but its time it takes to go through a certain number of pixels on your camera changes because of the way, because of its elongation angle. So basically, if the plasma packet is at 90 degrees to where the camera is pointing, it will spend the shortest amount of time in that section. Therefore, it will spend a short amount of time in those number of pixels. So it will have the same number of pixels in this area, it will just spend longer there. And so that's why the lines aren't straight. That means you get interesting curves depending on where you go. These tracks then can be, the shapes of these tracks can be then used with the mathematics to pull out this beta angle, its propagation direction, and its velocity. So ultimately, a JMAP technique is used by people to make an estimate of where the CME is going and how fast. Then there's a lot of different models on them. So we don't need to go through all of them here. But the basic idea is, in some of the first papers that were written looked at this and made the assumption that we're looking at a single plasma packet, so an infinitesimal plasma point in space, and how that propagates out. People try to address that limitation by identifying that a CME is a very large bubble, and what you see is not always the same point, meaning it's not always the nose. As the bubble goes through the heliosphere, you start sampling different parts on that bubble. And because of that, that makes unique changes to the mathematics. And that's kind of what's being addressed here in many of these different types. So you've got point P, fixed phi, harmonic mean. You can go into the details. They're ultimately doing the same thing, but trying to make small adjustments to the same core idea, which is velocity and propagation direction. Okay, so same idea here. I wanted to highlight here, this is the point I was trying to make in terms of you're not always sampling the same point. So if the spacecraft is here, and this is the circle, that's your CME. At this location, you'll sample where my green pointer is. But as this bubble propagates out further, you're not going to be sampling that point. The tangential between the stray light and the bubble will be different. It'll be a different point, and that's the key. And so that makes slight differences. So the harmonic mean assumes that the CME is a massive bubble where one of the edges is always on the sun. Okay. I wanted to show this movie. This is another methodology of trying to get an idea of its velocity and its general geometric structure. And what I'm talking about is the cone model. So I'm going to go through a variety of different methods for the cone models, different to the JMAP technique. And there are several different ways of doing that. And the object of the game in this situation is we want to get a handle of its geometry because we want to get an idea of how big they are, where they travel. And in particular, sort of like things like densities within it and where Earth will go through it and how the field lines are changing with it. And we can only best do that once we have a good handle of its 3D structure. So we'll start with the basic cone model. The cone model is done pre-stereo predominantly. And the idea is that you've seen this coronagraphic image, so back at the sun. You don't really have three views on the sun, as it were. You don't have stereo. You can't look back and triangulate. So you just got one thing, one image from the Earth, as it were, looking at the sun, and this CME is coming and hitting you. And what you're seeing is what's called a halo CME, which is effectively an event that circles the entire occulting disk. The occulting disk is the bit that's covering the sun, and if your event goes all the way around the occulting disk, that's considered a halo event. If it goes slightly less than all the way around, it's called a partial halo. But you can play around with some mathematics, and if you assume the CME is a bubble, a spherical bubble, then if you get a different shape, an ellipse in this case, and you know it should be a sphere, then you can play with some maths and create something that is effectively a cone model, and to tell you which direction it's now traveling in. And therefore, you can then pull out what its velocity is. Same idea, you can just add in an extra parameter effectively. And that kind of gives you a bit more degeneracy in the situation. But it's identifying the limitation that the cone model is a spherical bubble, and that's not entirely true of what a CME is. By the movie I was showing, it was that so-called croissant type structure, or a flux rope. And in this elliptical case, what you're really saying is the CME, let me go back to the movie. I'm going to stop it here. No. Okay, so here, this thing is not a sphere, right? It's not a spherical bubble. So while the cone model is practical, it has limitations. And in this case, if you treat this as what you want to treat it is coming out, I'm going to have to show it. It's a cylinder that's coming out from the top, coming down, and then coming back in again. And so there's the central axis of this is coming out here, down here, and back in. And so this component is this bit. It has a major axis. It's not the same as this bit here. And in that case, you're better off addressing your cone model by an ellipse. So effectively, an ellipse will have a major axis at the front end here and a minor axis here. And so trying to address that, you can create an elliptical cone model. That has a little bit more of a complexity in the mathematics, but it can still be done. Then there's a more intriguing, more realistic methodology, which has really become a very active methodology for using for science purposes. The circular cone is still predominantly used for forecasting, and I'll talk about that in a second. But for science purposes, you're probably at this stage still best off approaching the situation using this model. It's called the graduated cylindrical shell model, done by Arno Thurnesson from NRL, and it's within the SolarSoft package. So this is freely available, and you can just actively use it in IDL, and it's super simple. We've got a GUI and everything. And you can use it not only just for a single spacecraft, but it works in a triangulation format. And so you can create all three cameras from the stereo and from L1 and start playing around with this particular model and tweaking where it goes and how big it is and try to match the observations. And that really gives you a handle of what its size is. And in particular, quite recently, that's been modified. And there's a few teams that have tried to do this. And what they've done is they've actually incorporated that GCS. And they've done it in so that you can now add more than one GCS model onto the images. And you can add a shock model on top of it. And the shock model is in essence just a sphere. It's a dome, which gets added on top. So this is, in essence, an image of one time frame of using the GCS model in practice. And so what you're seeing here is in yellow is the actual GCS model, and the blue line that's going around this way is in the parallel, basically as close as possible to the surface of the sun, and then the red is what's coming, is the dome coming out. And so that's trying to identify the structure of the shock front. So if you're interested in the CME being erupted and you're interested in the shock front, the idea is you can try addressing both situations. And what you see in practice is the shock doesn't uniformly propagate symmetrically with the CME. And there's some interesting sciences showing behind that. But this is in practice of how it gets used. You've got 3 cameras from 3 different views. The center one was effectively the sun-earth line, and then your stereos from both sides. While that GCS is perhaps the most insightful that we can try to get for science purposes, it is much more involved and has a lot more parameters, and it isn't particularly easy to perform in real-world scenarios, or rather real-time. And we'll go into more of this in the lab later today, but this is an interface which you guys will see and start playing around with, I believe. Is that correct, Nick? Okay. Then a very similar setup to this, which is in practice how the forecasters kind of go in terms of triangulating using a cone model. But again, this is available, and since other stuff, you can go start playing with this stuff. Okay, so moving on to the second part of our talk, stuff that I particularly have been working on relatively recently for a while, and these are all the evolutionary concepts of what's happening in the CME. And so this is uniquely different to the initiation problem. We have lots of confusing information of how CMEs initiate, but we also get a lot of confusing characteristics that we observe of how these objects are evolving. And a lot of that is driven by not pre-stereo emission. So you'll have a lot of scientists that were heliospheric scientists that would look at only in situ data. And then you had the solar guys who would only look at the chronographs. And so an example of this summer school is trying to link in all that together. And so we've tried to get a good handle of what's happening in the evolutionary stages. So we're going to talk about that. As a way of, in terms of data and trying to get access to this stuff, we want to spend most of our time trying to do the insights for the science, rather than spending our time trying to find where the data is. So I've given you a large section of links here where you can just access data as efficiently as possible so that you can focus on the science. And these are the catalogs specifically designed for linking the remote to the in situ. And so what I wanted to highlight was, with all these catalogs, actually, we need to remember what we're trying to do is trying to be scientists, and we want to try to understand the insights that we can gain it. So you want to try to avoid spending all your time just accessing data. And I put a statement here. There's a couple of UK guys. And so if you did your PhD at Imperial, this is a phrase that was constantly harassed into you, like me, which was Professor Steve Swartz, smart guy, lovely guy. But he will always, if you ever give a talk to Imperial College, and Steve is in your audience, he will always sit there at the end and just go, "So what?" is his famous quote. He will just go, "So what?" And he will, if you just present to him a large collection of data that you prettily and forever collected, he will be very annoyed. He wants you to have an idea of the science behind it. So science is not just butterfly collecting, and that's an idea I want to say. Collect your data, that's great, but have some insight into it afterwards. Try to remember that's what you're trying to go for. There's lots of different concepts, and I'm going to try to go through most of them today. And I've identified effectively 8 core concepts, which will help you, I think, if you ever want to start understanding or trying to link different areas together. And so we'll start with deformation. Okay, so back before stereo, a lot of what we try to understand with the evolutionary effects between the sun and the earth was predominantly done by simulations. And our simulations weren't exactly perfect. And indeed, they're not really now. And we're always trying to improve them. This is some of the earliest work that Duchamp did on the NLIL model. So the NLIL model we've all been starting to use and see. And so this was some of the earlier stuff. And so the CME itself doesn't have a core magnetic field. It's basically just a pressure pulse or a density pulse. And if you do this and you inject your CME into a background solar wind, in this case, if it's inside the slow solar wind. So the gray section is your slow, and your white section is your fast. And depending on where you inject it, you'll get weirdly deformed objects. And a lot of that is because there is no internal magnetic field restoring it into or maintaining its shape. And so what you're getting here is, in this case, predominantly it's stayed in the slow solar wind, and it's what they call pancaked, so it's stretched out, as everything has to propagate radially away from the sun. And so it does these things called pancaking. But if you inject it into areas that aren't uniform, you'll get these very intriguing situations where things are going backwards. So in this case, the CME has gone very fast in the solar wind, but there's a certain element of it that's being trapped in the slow solar wind and gets trailed back, and you get these strange objects. Sorry. So quickly just going back one step, the idea of pancaking. So the idea is, if the CME is going into the heliosphere, everything should be moving radially away from the sun. And if you do that, then you automatically get this thing of flattening of this object, because what's happening is you're starting with this flux rope. So in this case, the axis of your flux rope, or your cylinder, is coming out of the page, and so you have a circle. And as it goes out into this heliosphere, it should follow these, each plasma packet should follow a radial line. So this point will turn out here. And naturally, from radial propagation, it will flatten out, because the expansion in this width will not keep up with the amount that is forced to pancake out this way. And in simulations, because there wasn't really any magnetic field maintaining this integrity, it will just get really squashed. We saw simulations where it became very, very thin, very much like pancakes, which is where the terminology came from. But if you look at intriguingly, if you look at some of the data, we have a handle of how much CMEs expand in this radial direction, because we have spacecraft that sit at these points, and the CMEs go over it. So we have an idea of how fast the CME is propagating, its bulk flow, and how much it's expanding, because we've got the time series of what the speed was at the leading edge and what it was at the rear edge. So we know its expansion velocity. And if you look at that, and we have a handle of what this value A is, and it's usually at about 0.1, so about 10% of expansion. And it doesn't really get that much higher. If you do that and you plug this in, you actually get something intriguing where you get this chi value is effectively its aspect ratio of this major axis divided by the minor axis. And you get these intriguing concept that while it does pancake, it actually would probably start ceasing to pancake. It will get to a certain threshold where it doesn't pancake anymore. And so while that isn't necessarily true, because the inherent assumption is this A value, it does give you a handle that some simulations where it's constantly showing pancaking isn't necessarily true. So and I looked at this and tried to get a handle on this, and I'll go into some of the details later. But all these data points are different CMEs that I looked into to get an idea of what that aspect ratio is. And if you go on that, this curve being the theory of where it should be, what you're seeing is actually getting a lot of scatter, a huge amount of scatter. You're not really seeing much below 1, which means it's not turning into sausages this way. But it's all underneath predominantly. It's underneath nearly always underneath the theoretical max, which is interesting. Oh, and sorry, I should say, if you can't see the numbers, Earth's radius is here, and so a lot of this data was through Ulysses. And another part of deformation, with the pancaking idea, you get a concave structure of as things move up radially. And what I kind of briefly alluded to with Dushan's model is, depending on which kind of solar wind you go to, you can get something really drastically weird. Although that's never really been seen in observations that much. And so this was intriguing that we could only really start to investigate once we had heliospheric images. And this is an example of the HI cameras where we're getting a CME that's this concave outward, where it's reverse pancaked. So it's going this way, opposed to a standard this structure. And this has only really started outside the coronographic fields of view. So what you're seeing in the coronographic fields of view is that it's predominantly still circular. And it's only when you start getting to the heliosphere where it's effectively interacting a lot stronger with the solar wind, it does something intriguing. And so this is an MHD simulation that we're looking at what the speed profile was. And this is the longitude where the CME is being ejected. And if you see this is the curve, effectively, of the solar wind speed. And at this point, where it's all very slow, is effectively the center of this CME. And it's going through these fast sections on the top and the bottom, creating this very strange deformation. Now, and then you go into the heliosphere, and people have tried to look at this through the heliosphere and within situ. And then there's people saying there isn't that much evidence of pancaking. And the reason is a lot of what you're seeing is not the same feature as you go through the camera. And in fact, it's perhaps just a projection effect. And what these guys were showing was the parallel expansion does continue following our standard sort of power law, which is done by Botham and Schwen in terms of its propagation. So parallel meaning parallel to the radial. But it's perpendicular, meaning, go back. So what they're saying, parallel, they mean along this line, and perpendicular, they mean out of the ecliptic. So what they're saying here is the parallel, so along the radial, it follows the standard power law, and that's fine. We're not really discussing that, and that's not that much of an issue. But the perpendicular expansion has more confusing aspects, which means the pancaking is starting to stop. They're suggesting out into the heliosphere. So that starts to corroborate the idea that our initial NLIL simulations, where it's continuously getting thinner and thinner, is not necessarily true. Okay, so deflections, part number 2. This is going back to the sun again. Now, if you look at lots of solar imagery and coronographic images, you'll start to see CMEs not erupt in a nice uniform structure that lots of schematics show. In fact, like schematics I showed. And what you're going to see in the real world is a CME will launch, let's say over here, and you'll have a large corona hole that happens to be slightly northeast of it, as an example. And that will start to push things in different directions. It'll have a inhomogeneous background, as it were. And these CMEs get launched into a complicated environment. In cases like that, you will start to see either bits of the CME or the entire structure moving in a non-radial way and effectively deflect. And so there's an example of some of these events where you have the CME and it comes out into the heliosphere, and if it was to propagate radially, it should follow this line. But in fact, you then see it in images when it's further down here. And so you have to account for this and try to get an understanding of what's happening. I should have mentioned, so there's a model that's trying to address this and trying to get a handle on how much it deflects on a mathematical basis. And it's trying to convert using the PFSS model, this basic sort of background solar winds, background coronagraphic model of the sun, and get a handle of how that's affecting where the sun, the CME should propagate. And they want to use this as a predictive tool, because if you know where corona holes are, and you have some sort of theoretical relationship of where the CME is, you might have a handle of how much it should deflect. Then we can go on to rotations, and this is interesting, of what I was saying earlier. If you've got something that's deflecting, well, how's that different to rotating? If you've got if you've got an object that's horizontal as a big cylinder, and you push this bit down, is that rotating or is that deflecting? And so then it starts to become just semantics. And so you want to start looking at the actual forces of what's causing different bits. And so the argument really is something, or an argument should be down to the forces. And if you look at, if there's a particular macroscopic property that's forcing the entire CME to move, then that should be considered as something that's being deflected. If it's happening on a more local scale at certain components of the CME, then you consider that to be rotating. And in this case, this is a different case of why the object is rotating, not down to background, but in fact just through the release of CME, and you're getting current sheets forming and actually causing a torque. And so as the CME comes out through this MHD model, you're seeing these flux ropes. What was a donut? I should stop. Oh no. I'm going to stop this here. So you start here, and you can see you've got a donut. The central axis of the donut, actually where the green dot is coming out of the page. And what you see, once you've got the torque, which is what we're kind of highlighting in these places, it twists the entire object into a complete 90 degrees, where you've got at this point, that axis is now vertical. And these kind of things that are actually seen on observations, you do see CMEs rotating. How much they rotate is under debate. People have shown quite varied amounts of rotation. How and why they are caused is certainly under research. And trying to get a handle on even just an average amount is not quite known still. This is a movie I just want to show where observationally we first started seeing rotations in the chronographic images. And this was what Anglos was showing, that you can get rotations quite early on. And he was using, so I wanted to highlight this mostly for the GCS model, as well as the rotation. You don't really necessarily see the rotations. A lot of the rotations he was showing was happening further out, but I wanted to show it at these heights for the GCS model, which I was highlighting earlier. So you've got your three fields of view, and you create this GCS structure, the CME structure, and you can overlay it on the actual observations so that it fits well. And you can try mapping it out between the cameras as it gets bigger. And so we're just going to, so you can kind of have an idea that if you can do this well and triangulate it, you can get an understanding that it is in fact rotating, and it's not, you're removing out other uncertainties from being able to triangulate and being able to check from all the different images. Sorry, I'm not going backwards and forwards very well. But you can do that yourself. Sorry. Okay, so there is this idea, at least for simulations, that you can get torque close to the sun and it should rotate. And you can see this in observations in coronagraphs. And then you go, well, if it's doing that there, should it still continue rotating out into planetary distances? Should there be a point where it stops rotating? And that becomes much more difficult to do because you can't, it's not as easy to do the triangulation with GCS out into the heliosphere. And then you're limited to other tool sets, basically. And one of them is using flux rope fittings with in situ data. And they tried to do something similar to that, and they got this. Oops. where effectively, sorry, the green's not come out very well. The green is meant to say in situ, and so the direction of your axis of your CME, so the central axis of your flux rope, how that's orientated in terms of angles and position in the heliosphere is shown as the green dots. So this is its tilt effectively. In situ is green, and in the remote sensing and the images it's red. And so they've highlighted how much it's changed between the chronographic fields of view to the value, which is about 40 solar radii, 30, 40 solar radii, and how it's changed from that, which is red at 30, 40 solar radii, to in situ, which is 215 solar radii, which is the green. So you've got about 150 solar radii of evolution happening between the red dots and the green dots. Now, there's, again, lots of assumptions that go into estimating what the orientation is within situ data. But what's clear is that it's not necessarily that simple. You're getting a lot of variability, and that's either down to the assumptions or that perhaps there is some other forces that are actually acting on this. Okay, and then we'll go to topic 4, reconnection. So I've got 2 topics here on reconnection, as it were, basically on different scale sizes. And what the first one is, what it's really called in papers is a flux erosion. Different to what we're talking about as flux erosion in terms of the initiation process, completely different. But what's effectively happening here is somewhere in between the heliosphere, somewhere in the heliosphere, the amount of flux of the CME is going to change. It's either you're going to either get more pileup and it's going to somehow wrap around, perhaps, or perhaps it's going to get eroded by reconnecting with the background solar wind. All you do know is generally CMEs do interact with the solar wind. And so an idea here by Alexis Rufinek and Benoit was that you can get something called flux erosion on the front side of the CME. So in this case, this is your flux rope, the axis coming out. The sun is where my green dot is on the right-hand side. And the solar wind's over here. If this CME is going fast, it's pumping into the background solar wind. And depending on how that's orientated, you can reconnect the background solar wind that's leading the CME with the actual flux rope field. And in that case, you can conceptually go with the idea that you've got reconnection, and then that means that erodes the flux of this particular CME. And in such a case, the idea is, well, if that does happen conceptually, how can we measure it and prove it? And what they did was, well, if a spacecraft goes through this dotted line, there should be an inequality of the amount of magnetic flux that we see in situ data. So effectively, if you look in just this diagram, the amount of closed loops on the front side of the CME is 1, 2, 3, because this is reconnected. But on the rear side, you've got 1, 2, 3, 4, 5. And so you've got more flux, as it were, on the rear side than the front side. And so that's what they call the sort of excess flux that they're talking about. So if you look at it in situ data, and you can identify when the start and the end is, if there's more flux in the rear section of it, then you get a handle on perhaps that some of the front section of the flux has been eroded away. And looking at it in a 3D perspective, that's what they did here as a schematic. And what does that mean in 3D, and how does that affect the field lines is an intriguing problem in terms of the amount of twist. And so these are some schematics that they try to create as conjectures. Okay, so I've got break time here. So I think that's probably a good place to go for a quick break. And I've got this link. Well, you can take a break. This is Benedict Cumberbatch. Oh.
Jets of superhot gas rising waves of fire. The most violent explosions in our solar system.
Oh, thank you. Yeah, you can watch the movie. You got to watch the movie. Silly. Sorry, I was getting excited by it. Wait, no. Benedict Cumberbatch is Sherlock Holmes. Potato. You hearing
A
that?
fury is building on the surface of the sun. Jets of superhot gas. Rising waves of fire. The most violent explosions in our solar system. Journey into our star. To explore its inner workings. And experience the power of solar superstorms.
Ready, light is on.
Is it playing right now? Oh, cool. Okay, everyone back again? So let's crack on. If I can get this to work. Perfect. Okay, so we did, we're talking about reconnection in the CME. I gave you one of the examples, which was this idea of getting some reconnection happening on the front leading edge. Clearly, the same kind of mechanism can happen on the rear edge, but I just showed one example of it happening on the leading edge. There's another intriguing concept of having reconnection, but on a much more macroscopic scale of the entire CME. And what is described is more like a current sheet. So conceptually, you can think back to the idea of what we had as a pancake. So you got the CME. It was a cylinder, a circular cross-section cylinder. It pancaked and became flatlined, and it flattened. And if you do that, what you're doing with the inner field lines, effectively, this inner field line, this circle, is going, let's look at it here in this example. At the rear section, so the sun's here, propagating out this way to the right. The inner field line, the loop is, on the rear side in this case, is going up, and the front side is going down. And so that's anti-parallel field lines. And if you squash them together and you create the pancake, what you're getting is, if you ignore the top and the bottom, what you've effectively got is a field line going up and a field line going down. And you're squashing them together. And in effect, you're creating a current sheet. And you're getting an increased current density. And if you do that, then you can conceptually get an idea that you can get these current sheets that form inside CMEs. And then if you really think of, in extreme cases, and conjecture of what happens if you have these extreme pancakes, and you get a case where you've got a current sheet start forming, you could conceivably think, well, in a complex scenario, if you've got a current sheet somewhere in this CME and you've got interhomogeneous solar wind happening, perhaps that will drive something even more drastic. And in a case like what was kind of suggested here, in the very extreme cases, well, you'll get reconnection in that current sheet. And then that will get you basically islands. And what you'll have is, you had this one entire CME, maybe it's possible to disintegrate it into multiple CMEs. So then there's what I described here as a plasma beta transition. Not entirely the right description, but it was the best title. There's some work done many years ago that looked at CMEs erupting through the solar surface. And so they did a simulation of basically below the solar surface of a flux rope. And it was a circle behind this panel of the initial state. It was done in 2D. And they, through just general buoyancy, this flux rope started rising through effectively the convection zone. And what they were finding is, depending on the amount of poloidal twist, this flux rope will start to disintegrate. Meaning, if you think of flux tubes inside a flux rope, so you've got a flux rope, and this is, I'm going to describe it with the aid of my trusty Bluetooth thing. Okay, so this is your flux rope, and what you're seeing is the circular end. Okay, and in this case, if you've got lots of poloidal twists, a flux rope, so a field line that's twisting around this object, then that has a restoring force and keeps that object together. But if you don't have that much twist, you just got effectively the toroidal or the axial field. What you've effectively got is you're holding, lack of a better word, a bunch of straws all pointing outwards. And if you throw a bunch of straws upwards, there's nothing holding it together. There's no twisted rope around it holding it together. So you've just got a bunch of straws and you just throw it up, it will just disintegrate the edges of it. And that's effectively what's being shown here. In this case is that you had this effectively like a bunch of straw pointing outwards, this page, and it's being thrown up. And by interacting with plasma above it, it just pushes out the layers behind it and disintegrates your object. And what's interesting is if you look at the mass behind it, is actually something called this Weber number. And you can get a handle of when it should or should not disintegrate, effectively defined by the relative velocity of the background to what's being thrown up your flux rope and the alpha in speed. And it's basically coming down through the ratio. Well, so that is effectively coming down through the ratio of the kinetic energy density, i.e. the amount that the CME is moving, and the colloidal energy density, which is the amount of twist on the outer edges. And depending on where that ratio hits 1 is where your CME will start to disintegrate. And so that boundary is what we're showing is here in those earlier images. And what you're saying is if you decrease the amount of colloidal twist, meaning it becomes more like a bunch of straws coming out, a bunch of straws being this scenario and lots and lots of twist being this scenario, you get basically a situation where you've got no flux left in your flux rope, and it's all back in these weird wings. So I had a go at doing this with solar wind parameters, or closer to solar wind parameters in the heliosphere. And things appear to be much more complicated. They help with the idea of creating pancaking structures. You clearly see the object pancaking out. And in this structure, this thicker white line is effectively the boundary of the CME. And so you're getting flux coming out, and you get this concept of pancaking. So if you look in the heliosphere and you see, effectively, you wouldn't normally see the flux rope itself, but you often see the envelope surrounding the flux rope, the sheath region. That would be pancaked, because that would be the structure between a shock front, in this case, out here, and the flux rope, and that would be pancaked. So what you'd see is a sheath region, and you would see it pancaked. But if you actually looked at the flux rope itself, in the observations, you don't see the flux rope. What you see is a dark cavity, so a void, when you're looking at heliospheric images. So all you know is the overall structure of this void is pancake, but you don't really know what's inside it. And so it's intriguing that this simulation can kind of show that you've got these wings happening, but a lot of your flux are remaining somewhat circular. And in this case, that kind of corroborates some earlier work I was showing. If you're looking at the aspect ratio, I was showing things potentially for pancake, you should go to that 4:1 ratio. And I was showing in situ, there's a lot of scatter of what this aspect ratio should be. And so this is an example of why potentially you might be able to get some aspect ratios that's much smaller. Because in effect, if a spacecraft went through this object, it would see a much more circular object and not so pancaked. So the results, and this certainly requires more study and isn't solving everything. One of the reasons why this was, one of the reasons why this was more complicated than the earlier simulations done was that there's a shock front in this situation. And in the earlier simulations, below the solar surface, the flux rope was just naturally, through buoyancy, just rising up, which meant the flow coming into, if you went into the reference frame of the CME, meaning the CME is not moving, then the solar wind's coming down at you, coming into as a plane of stuff coming onto you. In this situation, because you've got a shock, solar wind's being deflected in different directions. And so the solar wind coming onto you is not coming to you as a plane, and it's coming to you at different directions. And that complicates matters of what the CME or the flux rope is seeing, and how much of this object is becoming twisted, and where this magnetic Weber number boundary should be. Another interesting problem is a comparison between magnetospheres and CMEs. We had we'd seen this diagram earlier, and I can't remember which one of the lecturers showed this earlier in the week. But it's an idea that if a CME is a magnetic bubble, well then so is an Earth's magnetosphere. They're both just magnetic bubbles. You don't really care about or don't necessarily need to know what's in the center of this, in this case, Earth. So if that's true, it's been conjectured that, well, we can treat the magnetosphere as a magnetic bubble and just call that a CME. And then we should have similar characteristics in terms of the shock behavior. And if that's true, and this was some earlier work that was done pre-stereo, is that, well, okay, so what do we have with in situ data? Well, we have a spacecraft that cuts through this in one dimension. So in effect, a spacecraft will come through from the left to the right, and it'll start detecting solar wind as a time series. And in this case, you'll first hit the shock. And at the shock, you can measure the shock normal and its Mach number. Then, as the spacecraft continues to go through, you will measure the time that you're inside the sheath region. So this distance here, between the shock front and your magnetic bubble. And in that case, we can use the theory of the magnetosphere, or of its structure, and go, okay, if I know what this width is, then I can make inferences of what this height should be, perpendicular, because I know the geometry of what a magnetosphere should be. And if that's true, well, then at the next later point in time, you're going to physically go through the spacecraft. The spacecraft is physically going to go through the CME. So you're going to measure the amount of time you're inside the CME. So you're going to have the amount of time and the velocity that the object was going, which gives you the distance. So you're going to measure the size of the CME in this way. And you can use lots of assumptions and some maths and to get some inferences of what its perpendicular size should be through its shock standoff distance. And that gives you an idea of what you could be potentially looking for your aspect ratio. And I should start conjecturing. This schematic we saw was actually done almost half a century ago. And actually, there's a lot of assumptions behind that as well. And in fact, some of this basic mathematics that was taken on this was used from empirical relationships that had nothing to do with space, really. It was, in fact, done by throwing metal ball bearings through argon gas in a wind tunnel. And they got effectively this empirical relationship. And it's this empirical relationship, this 1.1 effectively, which was used into creating the theory between making some assumptions of how much this aspect ratio is of the CME. So getting an idea of what its 2D structure is from a 1D time series. And so this is going through some more theory of the actual the two-dimensional aspects of effectively trying to find out the aspect ratio, which we don't need to go right now. But what's intriguing is this equation, which is ultimately the point where you're trying to create this two-dimensional problem. And what's intriguing with this is that this idea of a magnetosphere being similar to a CME can be used in two different ways. One, which is the way I've described it here, which is this equation, your unknown variable is, in using it for in situ data, is this variable here. It's the radius of curvature, this perpendicular distance, the second dimension. But in remote observations, you know the two dimensions. You're seeing it with cameras. And in that case, your unknown is actually this Mach number. And if you don't know the Mach number, but you know everything else, then you can actually use the Mach number to make further assumptions. And that Mach number is effectively can be used into a scenario like this, and what I was showing in the first talk, which is you can use that Mach number with the geometry and the stock standoff distance, and you can make assumptions of the magnetic field strength upstream of the shock. And so then this can be done at lots of heliospheric distances away from the sun. And so what they've done here, this team looked at different CMEs in different images and to see what the magnetic field strength would be. And they did it here for very close to the sun using SDO imagery, and then here using heliospheric imagery. And they try to correlate it with, with what is the drop-off rate, the power law of how the magnetic field strength drops with distance. And they showed a rough power law, which is consistent of what we'd expect. So there is lots of this uncertainty in the underlying assumptions, but we seem to be getting something that seems appropriate. Okay, more of the theory we don't need to go into. And so finally, the last topic of concepts I wanted to work with today is continue looking with the shock fronts, but giving you an understanding of what this means for SEPs. So this was some work done by Alexis. Something unique that you can start doing with triangulation and looking at these CMEs from multiple perspectives in the solar wind, which is if you're getting previously those arguments with SEPs is are they coming from effectively the flare, which I guess we'll talk about tomorrow, and the flare reconnection, or is it coming from accelerated particles from the shock? And that's always been debated for a while, and it will continue debated. And both scenarios are occurring at for different situations. But can we prove certain events are coming from shocks? And that really can only be done in 3D. And what was great about this particular piece of work and the few subsequent papers that was published is that when you triangulate this object, you first can see by changing the color scaling of your coronographic images, you highlight where the CME shock front is, which doesn't seem to be great in this imagery, but you can certainly see it coming out here. Is that you can start creating that dome. If you remember what I was showing earlier with that GCS model, you can do the GCS and you can create a dome over it, which is your shock dome. You can start doing something like this here, and you get a handle of where this shock dome is and then where its effects would be on the solar surface. And those are things that we can start measuring as something called EIT waves, and people might hear that, and that's effectively a wave that's created from this blast of a CME, but it hitting down to the photosphere and being detected by observations. Anyway, I've kind of digressed somewhat. Yeah, I've only got these images. What I wanted to highlight was if SPs are detected from a process of energization from a shock, then it needs to be magnetically connected to the shock. And what's interesting is with this paper, what they showed was if you got from a particular event, you had right at the beginning a CME get launched, and an SEP was detected very early on at stereo A. And as the CME propagated out into the heliosphere, and you could see it growing in the coronagraphs, it got bigger, and so did the shock. And it did something called supraradial expansion. Does not matter. It's just a big bubble going out into the heliosphere. But at some later point, this big shock bubble then gets so large and so wide, it effectively starts to become magnetically connected to somewhere at a different longitude. And it gets magnetically connected at some later point to L1. And if you look at the SEP results at L1, you will start to see SEPs at L1. And what you're looking at is the timing difference between the SEPs detected at stereo A and L1 correlate to the timing difference between where the CME was magnetically connected to the first one to the time it took for this shock bubble to get to the other side of the sun. And so that was very intriguing in terms of being able to understand the longitudinal differences of SEPs. And this will continue being some under active research as we continue staying in solar maximum of how do SEPs vary with longitude on the sun, and indeed something called GLEs, which are ground level enhancements, which are very strong SEP characteristics. Okay, so moving to the third part of this lecture plan, which is going back to, sorry, yeah. The what, sorry? EIT waves. Okay, so the question is, what percentage of CMEs display EIT waves? I have to be honest with you, no idea. I don't know if there's been a systematic study of all CMEs and their associated EIT waves. Sorry? No, I don't. Oh, okay, so EIT waves and I think Moraton waves, and I think there's another terminology. There's a couple of words for these waves that were seen on the surface, and people were trying to understand what their fundamental physical process was. And I think I think the community is only starting to accept that it's predominantly shock driven or blast wave driven. And so I would suggest that there's no reason, conceptually speaking, why they don't all have it. But it really depends on the speed of the CME. If the CME is fast enough, then it'll have a shock or it'll be driving something in terms of a blast. If the CME is low enough in the corona and fast enough, it will then create the bubble that you need to detect it on the solar surface. If it reconnects too high up, like a helmet streamer blowout, then it won't be detected. Yes, that's what that is showing much more evidence for that. Perhaps there's other mechanisms, but that is what it's showing as mostly at this stage. Okay, so going back to, I'm going to now move to actually just in situ data. This is more of the traditional viewpoint of these interplanetary CMEs, pre-stereos, and what we're looking at. So I'm going to just skip over these quite quickly because they're kind of well known and somewhat constantly looked at. And within this in situ topic, I'm going to talk about 4 different structures, really. Catalogues, where you can get all your data again. The traditional properties, which is what I'll try to skip over a lot of. And then I'll start going into 2 more intriguing things, which is a slightly broader picture, which is arrival time prediction models, so for forecasting, and models of the actual flux rep itself as detected by in situ measurements. So we have an idea of what its analytical solution should be. Does that mean we have an idea of what its orientation is? Inherent 3D properties are once we have 1D data. Okay, so catalogs. This is the location of lots of catalogs, so you can pull out data. This is all predominantly just in situ. Lots of data of lots of characteristics from all the in situ data pegged into massive tables. So if you again want to do lots of studies on a statistical basis, this should be your first port of call. Okay, so the traditional properties. This is an intriguing one. No one has a fixed rule of what a CME is, at least, or rather, I should say, what an ICME is or an interplanetary CME is. No one has a fixed rule of what properties you should have. And that's because different CMEs show different behaviors. And so, so often some are shown, but not all of them. And sometimes a different combination of those some are shown. And so these are some of the ones I was going to highlight just as this was one particular example that seemed to have shown most of them. And this is quite popular event that people have shown many times before. So the magnetic field inside the CME tends to be stronger. Okay, that's the middle panel. The magnetic field tends to have a rotation that is effectively your flux rope, your twisted helical structure. And it tends to be less variable. It tends to be a nice, smoothly rotating object. You've got something called bidirectional electrons. And that's what happens if you've still got foot points, if your magnetic field line on both ends of your flux rope are both magnetically connected to the sun, then you can get energetic particles, you can get electrons that are streaming between the 2 foot points, so from the sun around through the CME and back to the sun again. And it can happen both ways. And so you can get something called counter-streaming electrons. And in this case, what that's effectively saying is this blue region in time is your bidirectional electrons. I should take a quick second, though. I'm going to simplify what this complicated diagram is. What you have is time on the x-axis, and then just lots of characteristics of solar wind stuff happening on the y-axis. Okay, so this panel here is just velocity, density, temperature, magnetic field, and angles. All it is you can just ignore all of them. You just look at one panel individually. It's just that characteristic in time. Okay, another characteristic that's popular and often used to identify the start and end time of CMEs is the proton temperature. It's usually lower in CMEs. So that lack of variability that you're seeing in the field line, that's kind of the same kind of concept. The object is moving very fast, but there's less variability. And so less variability, which is effectively saying less temperature. So it has a larger bulk flow, less thermal flow, so it's lower temperature. The velocity profile. This was what I was alluding to slightly earlier, which is the CMEs expand, often show expansion. And that means if they're expanding, that means the trailing edge is going faster than the leading edge is going faster than the trailing edge, which means you're going to have this a speed profile that's not flat. And often they show just a simple linear profile. Okay, so those are the characteristics, if you start looking at in situ data, that you want to start hunting for to identify your start and end times of your CME. So taking a broader picture of the in situ data, you can start looking at when the CME arrives at Earth. If you've done that, then you've no doubt probably have tried to detect it at the CME, which then means you're looking at sort of how long these objects have propagated to Earth. We have a rough idea that it takes usually between 2 to 4 days to get to Earth from the sun. Very fast CMEs can take perhaps about 18 hours, but they're under very unusual cases. But there's some interesting maths and some interesting science can be done on trying to understand how these things propagate in terms of velocity and arrival time. So effectively, arrival time is a space where the forecast is terminology for velocity, because the distance is the same and v equals d over t. And so they're basically the same parameter if you're trying to investigate that kind of characteristic. What's interesting is there are lots of propagation models. So lots of models, and I just grabbed this as a screenshot from NASA's Space Weather Research Center, CCMC website for all the different people and the different teams that are trying to predict the arrival time of CMEs. And most of them are actually employing basically the same theory. And it's a hydrodynamical case, and it's basically the v squared. It's the amount of drag force you're getting is correlated to the velocity squared. And this is theory that's basically hydrodynamic, but it works surprisingly well. And so they will all give slightly different values, but they're all, the majority of them are using the same underlying concepts. This is one example I wanted to show because this is useful if you want to start playing around with this. It's an online tool. There's a website where you can try fixing certain parameters to get an idea of arrival time. And so in terms of practicalities, this is something you can just go to quickly. Okay, and then the last concept for in situ stuff is the actual flux rope models themselves, and putting them, trying to model our flux CMEs from in situ data. So often, as an example, what in situ people are staring at is a stack plot. That's what this thing is. You've got stacks of lots of data. So a stack plot of all the characteristics of the solar wind, and you see a CME coming through, and you know there's a CME there. You have an idea, look, there's a linear profile of the velocity. There's an enhancement in magnetic field, and there's clearly some rotation that's smoothly rotating. And so you know there's something there, but you really don't have an idea of what its 3D structure is. We know we're aiming for a flux rope, but is it oriented perpendicular? Is it to the left? Have we gone above the central part of the CME, or are we going below it? And so that lack of understanding led to a lot of people trying to create models to get an understanding of these characteristics, or trying to pull that out from the data. And one of the first ones that was started to use something called the constant force-free flux rope model. And this was done Berlerga first did it, and Lepping optimized it so that you take the model and you optimize it to fit the data the best, and then you pull out what your optimized values are. And the idea is relatively simple. In this case, this is your schematic of a basic flux rope. The axis is coming out of the page, and the spacecraft goes through the flux rope from left to right. And that creates a certain profile of different points and certain characteristics. If you assume that you've just got a standard Bessel function as an example, standard, very circular cross-section flux rope. And in that case, you know what this should be, and therefore you can do something called minimum variance analysis. Don't need to know the details, but you can pull out what its axis orientation should be. Because in the theoretical case, one of the axes, the BX component in this case, should have no variation in its magnetic field. And another axis should have the maximum amount of magnetic field variation. And so you can pull out what you think the CME is orientated. By that, you can then create these models, which is effectively the black lines on these stack plots. Now, there's a limitation, like always, with a lot of assumptions. So that's the constant alpha force-free model, perhaps the simplest one you can get. And then people have tried to improve on that. So in this example, this is an example of you've got your magnetic field, but you can see this object expanding. This is the velocity profile here, and you can see it expanding. And so you know you're going to spend more time inside a CME at the rear end than you are at the front end, because it's expanded while you're inside it. And so you can modify your flux ropes to do that. An example of that was Marabashi that tried to do that similar thing, and this model is a replica of that. And then you can do some more intriguing things, like kinematically expanded. So you try to create something that's pancaked. So you take this circular structure and you turn it into a pancake, or something like this, and you do some math and you play around with where the vectors should move, and you can create something that's called a kinematically expanded flux rope model. And you do the same underlying concepts of optimizing to the data, and you pull out more intriguing insights. A latest one that's really come out recently is what I was highlighting earlier a little bit, which can be potentially used as an analytic solution to MHD, is a fully characterized flux rope, which is characterized by a lot more parameters theoretically, and it's trying to look into the current densities inside this object. And then lastly, something called the Grad-Shafranov technique. I haven't shown an image on that, but that is another methodology of pulling out some characteristics from the in situ data. Okay, so I'm going to have to be really fast in this. Bringing all this together, all these different ideas from the sun to the earth and all these different tools that I've tried to show as much as possible in the broadest possible way is how do we bring all this together and try to create some insights from all the different aspects. And so this is some work I've recently worked on, which is trying to do the BZ forecasting. And that's pulling in lots of the data from the solar surface and looking it out and trying to create the forecast. So this is an example. We were showing some stuff earlier, and I think we had some student talks that showed some stuff like this. This is a magnetogram. You've got positive and leading edge, and I've overplotted STO 171. And the red is basically your loops, your post-flare loops. And so we're looking at that, and you can pull some of this data, you get an idea of where the CME is. If you can do that, you have a rough idea of what its solar characteristics should be, its helicity, through some other assumptions. You know where on the solar disk it is. Let's say here is where it's erupting. You know where Earth is. You can pull out an assumption using the GCS model, the 3D structure, the croissant, or any of the other cone models. You get an idea of where Earth should be going through it. It gives you an idea of what kind of cuts you should be trying to aim for, what you should be doing as a 1D structure. So you have an idea of what its 1D structure is. So first, what you're going to do is you look at that solar imagery. You get a rough estimate of what its magnetic structure should be on basically that sort of idea of, you have an idea of what its structure should be depending on some underlying physics, its solar dynamo, or whatever its leading edge polarity should be. Second, you make that estimate, that volume estimate of where the Earth should be using data that's further out into the heliosphere, so coronagraphs, and you use cone models of some form. Then you need some more assumptions to estimate the total morphology further out into the heliosphere still. And that gives you an idea of this full CME structure, and you get an idea of what its axis orientation should be depending on where Earth is. And you pull out some assumptions and some values from that. And then you can then pull that out even further into the heliosphere and then take out all that information from the sun to the Earth and start to create that 3D structure and where Earth should go through that 3D structure and pull out your 1D time series, which is this. And so you can start creating predictions of your magnetic field as a forecasting technique. You can then take that one step further, and you take that magnetic field that you've just created, the red curve, and you can add that into more empirical relationships. As an example, you can put it into this, and this is the formulation that's being used by CCMC by converting their magnetic field, or their results from Enlil, and they convert it into KP. KP being directly correlated to the GS scale, which is your geomagnetic scale that NOAA are using for forecasting. So that goes, the GS scale goes from 0 to 5. The KP effectively goes from 5 to 9, same one-to-one mapping. You take that magnetic field, you put it into this equation, pull out some values, you can then create a time-varying KP estimate. So that's one approach on a simplified case of how you can potentially try getting these long lead time forecasts of the magnetic field. Another approach here is this is a model that some Japanese colleagues have been working on. They've got it now working in real time, and they're testing it. It's called the Susanna model, and it's basically Enlil, but the CMEs are now magnetized. And this is what we were hearing earlier with one of the student talks, is that they're also attempting to do something similar in creating an MHD simulation, which we can start using for forecasting. Okay, so then I've got into where should we go into the future, but I think I've run out of time. And so I think I'm going to leave it there and just leave you into these points. Actually, you know what? Let me just run through them quickly. Citizen science projects. People from the UK are doing that, very intriguing stuff. They're actually looking for some new ideas for their second Stormwatch, so if you have some great ideas, there's tools and widgets that can be used to do that. So go reach out. I'm sure they'll be excited. Planned missions for Orbit and Probe. I've got some YouTube clips figuring out where the orbits of these spacecrafts are going, and so you can look on them in YouTube and get an idea of what kind of interesting science that we should be able to do over the next few years. And that'll be important for you guys who will be coming into ending your PhDs and completing your first postdocs. These are the cameras, the wide field cameras that will be going onto Orbit and Probe, effectively. And then future, this is one of the movies. So this is Orbit and Probe, and this is a concept. People are thinking of doing an L5 mission. So here, in this case, Earth is sitting at this where my green spot is right now. And concept is of having a spacecraft at L5 to help with forecasting. And this is a movie done for when both Orbit and Probe will be moving around. The shaded regions will be when the cameras are on, so you can have a look. Unfortunately, the shaded regions don't seem as clear on this projector, but on the presentations and on the links on YouTube, you'll see them clearer. And so then I'll just finish off here, and I will finally say this is the finish. This is just the broader picture is economic impacts. And what's intriguing is out of the top 20, there are 5 US cities. Okay, thank you. Any questions? Great.